We have already mentioned the close relation between SparseLand and GMM and its affinity to a union of low-dimensional subspaces. Let's suggest another way of looking at this. Let's run another virtual experiment, again using the massive database of patches of size 20 by 20 pixels. We start by choosing an arbitrary patch, we call it x0. Now let's find all its delta neighbors and gather them as the columns of this matrix E. We will assume that this delta is very small. Observe that x0 is subtracted from each of these n columns in E. And now let's have a closer look at this matrix. Here is a very interesting observation. D, the effective rank of the matrix E, is expected to be very small, and definitely far, far smaller than 400, the dimension of these patches. A typical value of D could be 3 to 6. By the way, this will be true regardless of n, the number of neighbors. Amazingly, the above described behavior is expected to be true regardless of the choice of the initial patch x0, or even the signal source we experiment with. Why is this the case? Because our data tends to behave locally as a low-dimensional subspace of dimension D. Put differently, this means that when you have a valid patch x0, most of the change directions in the R400 space lead to visually unacceptable content, and only few directions are valid. The orientation and even the dimension of this subspace may vary from one point to another in the embedding space, suggesting that the data resides on a twisted low-dimensional manifold. What are the implications of the above? Suppose that we are given a signal z, a noisy version of x0, and our goal is to denoise it. We shall assume that the noise is additive and Gaussian. If we could find the subspace around x0, we could project onto it, and this would be a very effective denoising. Our problem is that for identifying this subspace, we need to find the neighbors of x0, but x0 itself is unknown. By the way, how come z does not sit on the subspace itself? Two reasons come to mind. First, the relative volume of the subspace is so small compared to the rest of the space that the probability for this to happen is virtually zero. Secondly, we know that the noise is uncorrelated with x0 and its neighbors, and geometrically this means that with high probability it is orthogonal to this subspace. So back to our story. We aim to denoise z, and the question is how to do it. Here are a few options in front of us. The first and perhaps the simplest is nearest neighbors. That is, find the closest neighbors to z and average them. The second option is to take these found neighbors and estimate the subspace they reside on and then project onto it. Both these options are tedious since they require us to have access and search in the full database of all the millions of patches. An alternative is to a priori cluster all the patches into k groups and simply project onto the closest of them. This is exactly the idea behind the GMM, in which we tessellate the data manifold into local subspace pieces. By the way, when k, the number of clusters, equals 1, this reduces to the well-known PCA. Clearly, for this clustering idea to operate well, we need large k value. Our last option is SparseLand based, where we start by identifying the dictionary D somehow. Given D, we apply pursuit that finds the best subspace and projects onto it. Due to the richness of the union of subspaces we get in this model, this approach has the potential to show competitive and even better performance compared to all previous methods.